special cases. Now, in this whole situation of system of forces, the simplest case would be a case that you have a set of concurrent force system, meaning that the line of action of all those forces pass through a specific point that you are trying to find the, let's say, moment about, right? Or they all pass through a specific point. So what I'm trying to say is that if I have, let me see if I can draw it here. Let me see, let's say I have a rigid body, two-dimensional space, and I have forces applied to this body, right? So the one is there, another one is here, another one is, let's say, is, I don't know if it's there, the other way. I care about the line of action. Now, if I draw some lines along these line of actions for these forces, I do my best to make them straight, but keep in mind they're straight, supposedly. I call this point O, right, where the line of action for all these forces intersect, right? So in this case, when we have a system of forces that all the forces intersect at a common point, that common point being point O in this case, right? I'll just call this F1, let's say F2, F3, can be more, F4, F5, F6, as many forces as you have. I put that under concurrent force system. Now in that case, well, let me just put a few words. A system of forces that, or better to say in which, I guess grammatically makes more sense, in which all forces intersect at a point. That point, this case being point O. Now what happens is that, well, this force system produces no moment about point O. You already know that. We said the moment is created when we have a perpendicular distance from the force or the line of action of a force and the point we are trying to find the moment about. Right? If the point is located exactly on the line of action of a force, no moment is created. D value, the distance, perpendicular distance would be 0. This case, it's located where all these forces intersect. So there is going to be no moment about this point. So pretty much, so let me put it, there will be no moment about that point. So to find the resultant force and resultant moment, right, for the equivalent system with only one force, which is the resultant force, and moment which is going to be the resultant moment, all you need to do is to find the resultant force. Right? There is going to be no resultant moment in that case. So all you need to do is just sum up the forces. I just put I, meaning that these are the summation of all the forces. Straightforward case, right? These special cases also, when we talk about these special cases, they help us to review what the general case was. Right? Every time I tell you a special case, I kind of tell you what the general case was. So I'm hoping that it's going to reinforce the whole idea that the whole process. Now the second special case, let's put this as 1. The second special case would be when all the forces are in the same plane. All right, just put it under coplanar force system. Coplanar force system. Now they're all in the same plane, like similar, close to what we had in concurrent force system, but well, concurrent force system, that condition does not have to be met. It can be in different planes as long as the let's not talk about that. Yeah, I don't want to make you confused. As long as the axis, if you're finding the moment on an axis, that axis is the axis that all the lines of actions meet. But forget about that. That's don't worry about that. So just talk about coplanar force system. So in the coplanar force system, as the name says, all the forces or lines of actions of all the forces lie or they are in the same plane. Right? That's the only requirement about this system. Now, what happens is that, well, obviously you're going to have a resultant force in this case. And because it's not the special case one and the lines of actions do not intersect at a specific point, obviously you're going to have a resultant moment. But the interesting thing about this, or not even interesting, something you probably notice about this is that Fr, the resultant force, and Mr, the resultant moment, are going to be mutually perpendicular. Let me see if I can draw. Actually, I have a picture. I can bring it here from the other textbook. I'll be lazy and use that picture, given that I have it. Okay, there you go. So for now, forget about this third one, just to make sure that does not distract you. I'm just gonna cover this. I'll delete it later on. But that's what I mean. And we have a couple of forces, F1, F2, F3, F4, you know, they are not intersecting, or lines of actions are not intersecting at a given point. So as a result, you're going to have some resultant force and some resultant moment for this system. Right? We saw this before. Right? There is no moment. So there is no couple moment or a free vector moment. So all the moments are created by these forces being moved to point O. Right? If point O is here, right, this force has to be moved here, F2. So this distance would be the distance we need to know to find the moment this force creates because of that moving. And then this force, right, has some distance, F4. So as long as we know this distance, once we put F4 here, we can find also the moment it creates and do the same thing for F1 and F3. So pretty much Fr, the resultant force, is the summation of all the forces, right, in this case. And the resultant moment about point O is the summation of all the moments created by these forces. I'm just going to call it Mi, I from 1 to whatever, as many number of forces as we have. As long as we know the distance, we can find Fd, or in three-dimensional space, R cross Fr, F. Right? Now, let me delete these. Now, so far, so good, right? This is not that special. But the interesting case, again, in this case, if you use right-hand rule, you will see that Fr is in this plane that we are finding all the forces are in. Right? They're all in the same plane. And Mr, right-hand rule, if you think about it, assuming that the Mr is in counterclockwise, so right-hand rule tells us that my thumb shows the direction in three-dimensional space. So moment vector is coming out of the screen. I'll show it this way. So as a result, these two are perpendicular. So as long as you have coplanar force system, the resultant force and resultant moment are going to be or better to say, they're going to be mutually perpendicular. Now, what happens is that, let me write a few lines here. Lines, in this case, lines of action of all forces lie in the same plane. Also, you have to add that Fr, or know that, as I said, and Mr, let me just put it MOR, follow the notation I'm putting there. MOR, right, these two are going to be perpendicular, or perpendicular. So far, these two things we know about this type of system of forces or force systems. The last thing is, what you can do, you can convert this. That's the new thing that we didn't talk about. You can convert this into, let me see. I told you I'm going to delete it now. I don't know how to delete it. Let me try. I shouldn't have made that promise. I should be able to delete this somehow, but I guess I just don't know. So I apologize. I'm going to bring the picture again because I don't want distraction about the first two parts we're talking about. So I'll just put it here again. Same picture as before. Let me just cover the previous one so things are not overlapping. Hopefully they're not. There we go. Now, look at the third one. What happened there is that what I'm trying to say, or this system, in this system, what this system I'm trying to say is that you can go even one step further in a system or an equivalent system that you have FR and MR, right? And convert it into a system that only has a resultant force. We can even move the force, right? This is the forces and resultant force and resultant moment about point O. You can find a point in this system that if you move your force to that point, you are not going to have a moment. Right? It's the opposite of what we did before. Do you remember when I was moving the force from one point to another? I said when you move a force out of its line of action, you have to put a moment to take that into account, take that motion into account. Now here I'm doing the opposite. I have a force and I have a moment in my system. I'll move the force around until the force, obviously out of its line of action, until the force is located at some distance away from the point that the torque created because of that motion is going to cancel the torque I had on the system. Hopefully it makes sense. Meaning that I do the opposite process. I move the force to a point that the equivalent system does not need a moment anymore. So I moved it the amount. You can think about it this way. I had this moment here, right? I moved this force the amount, and what happens is because of this motion, I have to put a moment on this system, and that new moment is going to cancel the initial moment. So eventually I'm going to have just a system with one force. So make it even more simple. Now, what is that distance? Well, that we can find. Because MO, right, MRO, we know that moment, whatever moment that I'm creating by moving this force should be exactly the same amount of MRO or MOR. I usually write it in MOR, but the book says MRO. They're the same. So the moments should be equal, so they cancel each other out. Right? So as a result, I know what this moment is. I know what the force is, FR, so I can find the value of MR. So I can say MOR, maybe I have to change it here as MOR, so things are less confusing, yeah? Is equal to FRD, right? The D that I don't know. So from there I can find D because I know what MOR is. MOR divided by FR. And that is the distance I have to move the force away from the point it was to get a new equivalent system with no moment. We don't need the filling on this one. So one step further, right? You could simplify a system already from a system of forces to a resultant force and resultant moment. Now you can even make it more simple, just one resultant force. as long as we move the force correct amount of length. All right. So that's about coplanar force system. Now we can expand this to three-dimensional space. I'll just quickly mention that. And that would be the third case. This is case 3, where we have parallel force system. Now, same idea, but in this case, forces that are, we say we have a system of forces that forces are parallel to one axis. Instead of last time being in the same plane, now they're parallel to one axis. Let me put it here. Bring the picture and use. Here you go. That's what I'm trying to talk about. Now, you can see the same logic. I have some forces. This is in three-dimensional space. I have forces F1, F2, and F3. Right? Look at these forces first. This is the original system, F1, F2, and F3. The equivalent of that, obviously, is going to be a system of forces. I'm going to have a resultant force by summing up the forces. And because I'm moving the forces all to point O, I'm finding the resultant force and resultant moment at point O. So if I move it this amount, it would be R3 for force 3, would be R2, it would be R1. Right? So this MRO or MOR can be found by just multiplying each force by the distance that force has from that point O. So eventually I'm going to get this equivalent system. Right? This equivalent system. Now, like in two-dimensional space, I can go one step further and get rid of the resultant moment by just moving the resultant force. Again, now I'm doing the reverse. I'm moving the resultant force to a point that the moment that force creates about this point, about original point, point O, cancels out the moment I had in the system. So I have a new equivalent system which only includes the resultant force. So you go from such a complicated, or I would say a system with multiple forces, to a system with just one force. Like up to here, we already did from before. Sure, this figure, huh? I can definitely do that. I just have to clean up a little bit. Actually, it's a good question. I don't know if I can. I might have to bring it again. So let me delete this one. I'll promise to learn how to do that if it's doable, though. So let me bring it back. I'm gonna make it bigger. There we go. Axis A and B are supposed to be, no, not necessarily. Axis A is pretty much just the axis that the moment that we have at the end is going to be in that direction. What is this trying to say is that even in this case, the moment that is produced is also perpendicular to the force, always, right? So let me write these here instead of keep saying that. This system includes forces that are parallel to one axis. In this case, axis Z. I don't know where X and Y are. So the resultant force is going to be parallel to that axis, right? Because F1, F2, and F3, they're all in Z direction. So positive, negative, the result would be in Z direction, either positive or negative. Now, the moment created by each of these are going to lie on this plane. Now, we can look at a couple examples, see that's always what happens. So let me just add that too, because this is a three-dimensional system, might need more explanation. So the moment produced by each force lies on the same plane. So what happens is that we have this moment, we have the force, they're going to end up being perpendicular. So FR and MOR, I'm going to change this to MOR, are perpendicular. Perpendicular. I missed so many letters in that letter word. Perpendicular. So the same process from here to here we already knew. We already knew how to go find this equivalent system. Now this step, this is new. This is a new step we are doing. We are following. You say, now I have a system with a resultant force and resultant moment. I want to get even a more simple system. How do I do that? How can I get rid of that moment? There. We can, the opposite process. Right? Obviously that moment, we can imagine that moment was created by a force. So what I'll do the opposite process. I move the force on the plate, find some distance d from the point O, that if I move the force there, the moment created by that moving, force moving, counteracts the moment we already have. So now I have a new system with only a resultant force. It's not an equivalent system by finding the resultant force and resultant moment at point O. It's an equivalent system that the resultant force has to be at some point d away from point O. How do I find that d? Right? So the same thing, but this time it's in three-dimensional space. I know MRO is, I have to write it in vector notation, d cross FR, because whatever that moment is going to be should be equal to MRO to cancel it out. So d as a vector, 3D space, would be MOR divided by FR. And that's how we can find that d value, where to put the moment, or sorry, resultant force, to have a new equivalent system that does not have that moment. So let me review what we said. I talked about three special cases. I'll go back to that page. First one was a concurrent force system. All forces are, they meet at the same point, they intersect, the lines of actions for those forces intersect at one point. There will be no moment. The second special case, or specific case you wanted to look into in more details, is coplanar force system. Set of system, this is two-dimensional, right? All the forces are in one plane, it's two-dimensional space. Obviously, the equivalent system about some point O is going to have a resultant force and resultant moment. The next step, I can make it simpler by moving the force FR, resultant force, to a point that the moment created by that moving force counteracts the moment I had from before. So I only am going to have a system with just one resultant force. And that force should be placed at some distance d away from the point O. I can find that d. The third case is the expanded version of the second case in three-dimensional space. If I have forces parallel, all of them are parallel, I can find the equivalent system from what we know from before, right? Just vector sum of all the forces and find the moment about the given point O. So I'm going to end up having an equivalent system with the resultant force, and a resultant moment. I can go one step further and move that force, resultant force, to a point d away from the original point and get rid of the moment I had in the equivalent system. So now I have an equivalent system. I made it very simple. I went from this multiple force to this system. It's just one force. as long as I put that one force D away from the point O. And that D can be found knowing MR, or moment, resultant moment, and resultant force. So we usually do this in the same order. We go from the equivalent system with the resultant force and resultant moment, and then go to the second equivalent system, which is simpler, and that is that can be found as long as we know resultant force and resultant moment.